Over the next few videos I want to look at how to program the MK14 microcomputer. But before I start, I just wanted to cover a few points that I'd seen on the various forums. There was some criticism levelled at the MK14 comments that it wasn't very well thought out, or that there were possibly mistakes in reproductions such as ours. And I just wanted to touch on those, that back when this was developed in the mid-1970s, the internet didn't exist. You couldn't just Google how do you program a MK14, how do you program an 8060 processor. Also, the budget for this was extremely small in terms of development, and again there weren't the PCB CAD programs we have today. Most of the designs were transcribed manually from one design to the next, and that inevitably results in errors between various revisions of boards. Although whether they were errors or not depends on the intent of whoever was developing that particular revision. The point really is that through the next few videos I'll be showing you how to connect various hardware devices to a MK14, and it is important to understand that not all MK14s are the same. It doesn't mean that any particular one of them is wrong, it just means that they're different, and it's something that you need to be aware of if you're connecting hardware. It's not unique to the MK14, almost all vintage computers are the same. I collect them and I have yet to find two of any variant that are the same, and that is certainly true of the MK14s. So to get started, the MK14 is actually quite a capable computer. It's very limited by today's standards, but when it came out it had some very nice features, relatively easy to program in terms of the code. But what made it very not difficult but time consuming and a little bit tedious to use was the monitor program. Also, the PROMs are limited to 512 bytes in total. That's for the entire monitor program. So it is limited in terms of what we can expect in terms of features for that monitor program. But even so, it's still very tedious to enter other programs into it. So for example, to enter a value into the memory, you had to first select the starting point for the memory, and then for each value you wanted to enter you had to press the term key, enter the value you wanted to put in that memory location, press the term key again, and then press the memory key to step on to the next location. So it's like 4 or 5 key presses at least for every value you wanted to enter into the machine, which is fine for very small programs just for test purposes. But when you come to programs such as games, so the moon landing game that most people are probably familiar with extends to well over 250 bytes, and typing this in manually is a very tedious process. It takes a long time, very error prone, and the chances of you getting it right first time or second time or even third time are remote. And then of course when you turn the MK14 off, it's all lost, and you'd have to start again the next time you power up the MK14. So what I'm going to show in this video, before we start looking at programs and what the MK14 can actually do, is a better way to get software into the MK14. So we've seen the MK14, I think most people that have one are familiar how to use it. What I'm going to do in this video is show how to connect it to one of these. For anyone not familiar, this is an OP-80 punch tape reader. Now obviously it's far more convenient to take a punch tape, so I've got a tape here that is actually the moon landing game, and I've transcribed the moon landing game and created the punch tape from the code. So when these two are hooked together, it's simply a case of entering a small reader program into the MK14 and then running a tape through the reader. Okay, so the first thing that needs to be done is to figure out how to interconnect them, and there are of course many ways you could go about doing this. If we look at the OP-80 schematic, then what we have is 8 data bits, one for each of the holes in the tape. We don't directly read the sprocket hole. The sprocket hole is actually used to set a latch, and when the latch is set, then it's assumed by the reader and any device using the reader that there is data available for the machine to read. So the host machine will then acknowledge that it's read that data byte by toggling the ACK line. That will reset the latch, and then when the tape hits the next sprocket hole, it will relatch, and then the host machine can wait until the RDA line changes state. It can read the next data byte, and then it continues until there is no more data. A couple of small issues in creating this. Firstly, it needs to know when to start reading actual data. So when you feed a punch tape through, you have this leader, and it can be any nominal length, arbitrary length. So your interface needs to ignore any data up to the point when it starts to read the actual program data. In order to connect the OP-80 to the MK14, you will need the optional in-out chip fitted. The in-out chip has two 8-bit ports, and they can be configured in various ways. They can even be configured to generate automatic acknowledge signals, but I decided not to use that method in this video, simply to keep the explanation as simple as possible. So the way I've connected them together is I'm using port A as the data input port, and I'm using port B as the status port. So if we look at the program that I wrote to handle the connection to the tape reader, so this is basically a simple tape reader loader. You can see that in total it's 44 bytes, or 38 bytes if you remove the optional LED status indications. So in this form that it's printed here, it actually uses the spare LEDs on the OP-80 to give various status indications. But if you don't want that, you can reduce this to 38 bytes. So as it says, we have port A uses data input, port B bit 0 as the acknowledge output, port B bit 1 as the ready input signal, so that's the output of the latch on the OP-80 to let the host know that there is new data ready. Port B bit 2 is the drive for the acknowledge LED, and port B bit 3 is the drive for the waiting LED. I'll explain what these LEDs do in a minute. When I say drive, they're just control signals. There's actually a buffer on the OP-80 that provides the drive current for the LEDs. So the way this works is very straightforward. It uses two pointers within the MK14. The first pointer is used to decide where the data is going to be written to. So when you enter this loader, what you have to do is change these two values to the start of the program entry point that you're loading. So in other words, in this example, the first byte of the program will be located at 0F12. So the first block of code loads that pointer, and we're using pointer 2 for that function. Notice here where I've put the address. What I wanted with this loader was to be able to reuse it without having to re-enter it each time I loaded a tape. So it's up to you where you actually load this. It is relocatable in this form. But what I tend to do is load it into the in-out RAM. So that's the optional in-out RAM that resides within the in-out chip, and that leaves your standard RAM and also your extended optional RAM free for programs. It also means that if you run programs from your basic RAM, then once you finish with one program, this loader will still be resident in the in-out RAM, and you can reuse it to load another tape without having to re-enter it. So in other words, once you've entered this once after powering up the MK14, you can just keep reusing it to load multiple tapes, and it will be in memory until you either overwrite it or until you power off the MK14. Gives a huge advantage entering 44 bytes once at the start of a session with the MK14, and then being able to load 5, 10, 20 tapes is obviously going to be a massive time saver and really makes the Mark 14 far more usable. Okay, so once we've got the first pointer loaded, we then load the second pointer. So this is pointer 1. And what I decided to use this for was as a pointer to the in-out registers. That's the in-out chip registers. You could use another pointer for the various addresses that you want to write to or read from, but because there is a number of different addresses that I wanted to read and write, I decided to use a pointer with a base value and then use a displacement to indicate the particular register or address or bit that I wanted to read or write. So this is loaded with the base address of the in-out chip, and if we look at the memory map for the Mark 14, you'll see that what we're actually doing is loading this address, which is the address for the in-out chip. You'll notice this appears in various places, and that's just because the address bus is not completely decoded. So you could in theory use any one of these, but I tend to find it's more reliable if you use the address at E00, and then all the ports are accessed through addresses in this range, including the RAM, which resides from E80 up to EFF, which is why I've used that starting address. Now, if you wanted to make use of the first part of the in-out chip RAM, then what you could do is relocate this right to the end of that block of RAM, and that way you'd even have some of that RAM available again without overwriting this loader. So it's only if you need absolutely all the RAM within the Mark 14 that you would overwrite this. Okay, so once we have the two pointers loaded, the next thing we want to do is configure port B. Now by default the ports are both configured as inputs, so we can leave port A alone, and then port B we configure the bits 0, 2 and 3 as outputs because we need them for the control lines, and then port B is the input, which is the ready signal. So if you want me to explain, by the way, how all this works and what each opcode does, then drop a comment and I'll go through it in more detail, but otherwise I'll just skip through and say what each block of instructions is doing. Okay, next thing we do is to turn the acknowledge LED off. That's the LED on the OP-80. These are the two spare LEDs indicated as S1 and S2. And then we turn on the waiting LED. The waiting LED is illuminated once the program is started, the loader program, until such time as it reads a non-zero data byte. In other words, it stays illuminated until the first byte of the program is read from the tape, and then it goes out, and that will indicate as you pull the tape through the reader that it's actively reading the tape. The next block is a small wait loop, and it constantly reads the ready input bit, and it waits until that bit is set, and it just keeps looping around until that bit becomes set. And as I said earlier, that bit becomes set when the OP-80 encounters a sprocket hole as the tape is pulled through the reader. Once the sprocket hole has been found, then we read the data in through port A, and for the first read, so this is the first byte that it's reading from the tape, it checks to see if that byte is 0. In other words, is this still the leader? And if it is still within the leader, then it jumps back to this loop, and it just keeps running around this loop. First loop, it's waiting for the sprocket hole, and then the second, it's waiting for a non-zero data byte. And once it finds that, then we know we've found the beginning of the actual program, so it moves on. Turns off the waiting LED, so the LED will go out to indicate that it's found the first byte of the program on the tape, and then it will save the byte it's just read to the location given in pointer 1, which is what was set up here. this instruction also increments that pointer, so it now points to the next memory address, ready to save the next byte that's read from the tape. It then toggles the acknowledge line to reset the latch on the OP-80, and that way the program will know when the next sprocket hole is read. Once it's reset the latch on the OP-80, it then runs through another small loop waiting for the ready line to go high again. Remember, this ready line is controlled by the latch that we've just reset, and it just runs around this until the next sprocket hole is encountered. Once the next sprocket hole is encountered, it doesn't matter if it's a zero value now, because it might be a valid zero value within the program, so it just now blindly copies all the subsequent bytes into incrementing memory addresses, and then it loops back to this point where it saves that value, increments the pointer, and it just keeps running through this, reading each byte from the tape, saving it to incrementally higher memory addresses, and it will run around this until the tape ends. Once you get to the end of the tape, all you do is you press the reset button on the Mark 14. That will stop this program, and then you can run the program from the address that you entered here. So this is the program from the tape, and it's as simple as that. If you want to read another tape, then all you would do is restart this loader program, which in theory should still be in memory, and then run your next tape through. Once you've run the tape through, press the reset button again, and then same as before, you would run the program by running from the start address that you entered into the loader. You might need to change this between each tape if the program requires a different start address, but other than that, that's it. It's very basic, fairly simple. If you do encounter any problems, you may need to enter some short delays between when the sprocket hole is met and the read of data. So if you find certain bits won't read reliably, and you've tried adjusting the light source on the OP-80, then most likely what is happening is the head in the OP-80 might be slightly skewed, in which case it could be encountering the sprocket hole before some of the bits at the end of the tape have had chance to be read. So in other words, if we look at the tape, I don't know how well this will show up on the camera, but if the sprocket hole is encountered and the tape is offset, imagine the tape is going this way, then the holes, especially ones towards the edge of the tape, might not be in the proper places to be read reliably. Now, the tape can only be offset by small amounts, but we're talking here about a microsecond or two, so even if there's a very small offset in the tape, you may need to introduce a couple of short waits, half a millisecond or so, between the point when the sprocket hole is encountered, which is at this point, and before you read the data, just to make sure the tape has moved fully into position. The types of thing you'll see if that is the case is the bits, especially the bits towards the edge of the tape, may not read at all, or may read intermittently. So for example, instead of seeing a value like 9, you might see a value like 1, and if that is happening consistently, then it's unlikely to be the light source that you're using. It's more likely that the tape is slightly skewed in the reader. Okay, so I'll now get the two bits of hardware connected together, and we'll come back and have a look at how to make it work. So we now have the OP-80 connected to the Mark 14. I made the interconnections as I indicated. Port A is connected to the data lines on the OP-80, and the various bits that I identified are connected to the appropriate bits on the OP-80. One thing I should point out here is I've made a slight modification to my OP-80 because I didn't want to have to use two separate supplies, one 5V supply for the OP-80 and one 8V supply for the Mark 14. What I've done is I've put a voltage regulator inside the OP-80. There is a spare pin on the OP-80, it's pin 12, it's not connected to anything normally. So what I did is I connected the lead going to that pin to the power input of the Mark14, which is fed normally from 8 volts on my power supply. And that comes into the OP-80. It goes into the input of a 5 volt regulator, and that 5 volt regulator output is fed to the plus 5 volt pin on the OP-80. So in other words, I can just connect the OP-80 to the Mark14 and it will work fine. However, because the connections at the socket on the Mark14, I've used separate pins for the power going to the OP-80 and the ground line, it means they're connected to the incoming power only because the pins are shorted on the Mark14. So in other words, if I unplug the Mark14 connector, I can still use the OP-80 with an external supply. Okay, hope that makes sense. So now we've got this connected, what we can do is power it up and then make sure it works. So switch it on, you'll see they both come on at the same time. We have the Mark14 up and running, and we have the OP-80 running it as well. So what I will do now is enter the loader program into the Mark14. It doesn't take very long, but I won't bore you with that process. So I'll fast forward through that, and then once that's loaded we'll look at how to actually make it work and how to load a tape. Okay, so that's the loader program loaded, and we're ready to load a tape. So to load a program from tape, all we have to do is feed the tape into the reader, as I've done here, and then run the loader program. So we'll go through the program start sequence. So the program was loaded at 0E80. Start the program. Notice that the ACK LED has gone off and the waiting for data LED is on. I'll now pull the tape through the reader. You see that the waiting LED goes off, and once we pull the tape through we press the reset key. We can now examine the memory that we loaded the program to. So if we look at that and compare that to what the data should be, see that the first byte should be 08, and it is indeed 08, and if we scroll through the rest of the bytes we'll see that 50 is correct, 0, 99, 80, etc. So we've now loaded the moon landing game from tape. It took probably 5 seconds to load the game, maybe 2 minutes to enter the loader program, and now if we want to we can go back and look at the memory where we loaded the loader itself. That was 0E80, and we can see that the loader program is still resident in memory, so we can run it again and load another tape if we want to, and we can just keep repeating that process for as many tapes as we want to run through the Mark14. And it does make the Mark14 a far more user-friendly machine, and we can load programs in a few seconds rather than half an hour or an hour. Well, I hope you found that interesting. In the next video we'll look at actually running some of these programs. If you have any questions on how to connect the tape reader to the Mark14 or how the loader program works, then please drop me a comment. If not, we'll look at the programs in the next video.